All right, so continuing on, we're going to look at the warming mechanism. And basically we're answering the question, how does all this extra carbon dioxide that is being put into the atmosphere alter the climate? And again, we're going to go through these 5 steps. But before we do that, what I wanted to do is back up a little bit and just understand light a little bit more. And so light, and also, so light is one of a bunch of things that are kind of, as far as physicists go, the same thing, but you know, just sort of different versions of it. And so the light that we see with our eyes we'll call visible light. And so what is light? Well, light is a very difficult question. In fact, physicists have been grappling with this, and there's lots of different sort of thoughts. But for our sort of interest here, light is a form of energy. You know, and an example, it'll heat you up on a sunny day. And for us, the one that we pretty much have the most experience with is visible light, right? And so visible light is the only thing that we can really see. That's what our eyes detect. And so light is a wave of constantly changing magnetic and electric fields. Visible light, again, that we see is the smaller part, what we call the electromagnetic spectrum. And of course, this word is just because it's this sort of constantly changing magnetic and electric fields. And so our eyes are sort of set up to see visible light, right? But there's a whole bunch of other kinds of light, that I'll use that term loosely, that we can't see. Right, so the visible light is what we can see, but there's things like radio waves, television waves, X-rays that's used to get, you know, pictures of, you know, inside with your bones and tissues and things, infrared rays, etc. And so technically, these are all parts of electromagnetic radiation or electromagnetic waves. But sometimes, you know, I'll just be loose and call them light. Now, each of these waves has what's called a frequency, which is the number of peaks that pass by every second, and a wavelength, which is the distance between the peaks of the wave. This isn't super important, but it will be something that we'll talk about. The speed of light is super fast. I should be careful. The speed of any of these electromagnetic waves. And the energy goes as this is Planck's constant, h, times the frequency of the light. And this Planck's constant is this here, 6.626 times 10 to the negative 34 joules times seconds. And this is, we should say, the energy of one photon of light. But the idea that we want to start getting in our heads is that all these different kinds of electromagnetic radiation, they have different frequencies and different wavelengths, and the tendency will be that basically the higher energy ones will be at the higher frequencies, which kind of makes sense, right? The frequency is the number of peaks that pass by every second, so hopefully it makes sense that, you know, if it's faster, it's going to be more energetic. Here's just a little diagram kind of showing this whole spectrum. So again, here's the parts that we see, the visible light. And again, those all vary too. You know, the lower end of this is what we see as red, the higher end is violet, and all the way in between. But there's a whole bunch of others. So there's like radio waves. So in case if you ever use the radio yourself, AM and FM waves, or this frequency and wavelength. So you can see here the frequency and wavelength. Infrared is another kind of electromagnetic wave. UV, ultraviolet, right? So ultraviolet is another kind. X-rays, again, that we use to get, you know, pictures of inside of our body sometimes. And then at the very high energy side is gamma rays. And again, so what basically makes these different is different frequency, different wavelength. Our eyes see visible light, and, you know, most likely that reason is because that's what our sun primarily gives off. Right, and so our sun primarily gives us visible light, and so our eyes, you know, it's more efficient to see that kind of light. But in theory, all these different kinds of light are the same thing. So viewing objects. So one thing that we're going to talk about is that all objects emit electromagnetic waves, even us. The frequency of these electromagnetic waves, again, depends on the object's temperature, right? And so basically everything emits electromagnetic waves. And like I said, our sun emits in sort of the more of the, primarily in the visible region, which is why our eyes, it's useful to have eyes that see that. But here's down here is a picture of from an infrared camera, which sees infrared, which is what us as humans emit. And so that's why in the infrared pictures you can actually see humans, and they seem like they're emitting lots of stuff, right? And so when we see an object glowing, that means that its temperature is just right to emit in the visible spectrum. In this picture, right, these things seem to be glowing; they're emitting in the infrared spectrum. And when we see cooler objects, like when you're at home, basically you're seeing the reflection of light off of the object. So often there'll be two kind of things going on. Every object emits this radiation, but it also can be reflected. Light can be reflected. And this is why we see less at night, right? At nighttime, there's less visible light to reflect off of things. Now, so most objects emit radiation at all wavelengths, again, even us, but they peak at a certain point. And so for every object, you can kind of have like a little graph here of intensity versus wavelength. And so for this particular object, the majority of the radiation is at sort of between these two wavelengths here. And so again, like I was saying, for us, we emit primarily in the infrared, the sun primarily in the visible, and every object is just a little bit different, and it depends on the object's temperature. And so that's going to hopefully help set us up for the next parts of our discussion. Okay, so I get this set up to start this calculation now. So again, the first step is conservation of energy. In order for the temperature of the Earth to remain constant, the thermal energy that flows in must equal the thermal energy that flows out. And so we've discussed this before, that when the sun's energy reaches us, we're getting 1,360 watts per meter squared. Now over here, you can kind of think of the sun hitting the Earth. When the sun's light hits the Earth, it sees this circle of area pi r squared. And so I'm going to multiply that times pi times the radius of the Earth squared. And so what that does is that'll give me an area. So that's going to cancel out with the a meter squared and give us units of watts, units of power. One other thing to note is that the atmosphere of the Earth reflects about 30% of this radiation. So I'm going to multiply this times 0.07. And so what this does here is this gives us the power that the sun is hitting the Earth with. Okay, and so what we're going to do then is take that and equal it to the power that the Earth is emitting radiation, and saying that those two should be equal. And so let's go through and do that. And so that's that side there. Now, the equation that talks about again, like I was saying before with the light, every object emits radiation, and the equation we use for that is the Stefan-Boltzmann law, and it's the surface area of the object. So the surface area of the Earth is 4 pi Re squared times the Stefan-Boltzmann constant times the temperature to the fourth power. Again, this what we're emitting depends on the temperature of the object, and then this sigma is a constant, which is 5.67 times 10 to the negative 8 watts per meter squared per Kelvin to the fourth power. So again, this will give us, just like the above, units of watts. And so we're going to equate these two objects, and so these two equations. So I got 4 pi Re squared, Stefan-Boltzmann constant, t to the fourth power. What's really nice is I can then cancel out the pi r squareds in both cases, and I can solve for t to the fourth power, and I get 961 watts per meter squared, which again is just 1360 times 0.7 divided by 4 times sigma. And then what's great is we can take this and calculate what the temperature of the Earth should be. And when we do this, we get a temperature of 255 Kelvin. Now remembering that this is Kelvin, this temperature in centigrade comes out to be negative 18 degrees. Now in reality, our temperature is more along the lines of 288 Kelvin. And so there's this difference of about 33 degrees that we have to account for. And this difference comes from the greenhouse gases, which carbon dioxide is a part of. All right, so we have this temperature discrepancy, and what's going on? Well, that's where the greenhouse gases come in. So again, conservation of energy was our first point. Then again, an object with non-zero temperature will radiate energy. And we use that to find that the temperature, right, should be coming out to be 255 Kelvin. But then the sort of actual is this 288 Kelvin. And what's happening is carbon dioxide blocks infrared light. If you look at the carbon dioxide, it blocks infrared light, and the primary wavelength or type of light that's being emitted by the Earth is this infrared light. It's similar to us. And so the CO2 blocks it. And that's kind of what this picture is here. So this 255 is kind of this picture. With no greenhouse gases, the Earth's radiation just kind of goes out, and it's all equal. Everything's good. But over here with the greenhouse gases, they block some of this. And so the author kind of talks about how it's kind of like wearing a blanket. It sort of keeps some of that radiation in and keeps the Earth at a slightly warmer temperature here, again by that 33 degrees. And basically what's happening is as the carbon dioxide concentration is increasing, it's kind of like you're making a thicker blanket. In fact, an interesting example would be Venus. Venus has a really thick atmosphere of greenhouse gases and has a really high temperature. And so, comparatively, and so it's sort of the similar sort of idea here. And so, again, this extra CO2 blocks this radiation and again makes the temperature a little bit higher. And this is sort of, again, this is our warming mechanism.